that today's lecture is actually going to help solidify all the rest of chapter 3 that we've talked about. There's nothing new, it's just a summary about the equation that models the harmonic oscillator. So it was my double prime, by prime plus ky equals 0. M is the mass of the object on the spring. B is the damping coefficient, typically friction. K is the spring constant. So tells you how like soft or not soft the spring is. So we call this equation second order because it's got second derivatives in it. Linear because the y only has a first degree, and homogeneous because there's no constant term. So we've thus far developed two ways to solve second order linear equations. One was lucky guess. We did this quite a while back, chapter 2. And the other was to convert it to a system and solve with the methods of chapter 3, which is finding eigenvalues and eigenvectors and using e to the lambda tv. All right, so we're going to solve one using both methods. So we can review lucky guess and we can review the chapter 3 methods. All right, so one lucky guess. For the harmonic oscillator, we said, okay, well, you're adding together a second derivative, a first derivative, and the function itself and getting 0, which means those three functions would have to all be like terms. So our guess is that it's e to the something t, something exponential. So we guess that there is a function y equals e to the st that solves this thing. So that means that y prime is s e to the st, and y double prime would be s squared e to the st. Then you take your y prime, and your y double prime, and you plug into your differential equation and solve for s. Figure out what s will make that an accurate guess. So y double prime is s squared e to the st plus 7y prime, so that's 7s e to the st plus 10y 10 e to the st equals 0. So I'm just plugging into the differential equation, substituting the things that are related to the guess. Every term here has an e to the st in it, so we factor it out. And we're left with s squared plus 7s plus 10. E to the st can never be 0, right? An exponential can never, there's no t that I could put in there that would make that term 0. So you could think of it as dividing both sides by e to the st, or you set each factor to 0. E to the st just is never 0. So next line is s squared plus 7s plus 10 equals 0. And that factors to s plus 5, s plus 2. So there are two values of s here that will make my guess a real solution. So I have s equals -5 and -2. So those are two, I've now found two particular solutions using lucky guess, -5 and -2. So I have y1 is e to the -5t, y2 is e to the -2t. In chapter 2, this is where we stopped. We said, okay, we found two particular solutions. But now from the work we've done in chapter 3, when you have two particular solutions, you can use them to create the general solution by taking a linear combination. Right, so my general solution is a linear combination of those two particular solutions. So y of t is k1 e to the -5t plus k2 e to the -2t. All right, method 2, system. And use the methods of chapter 3. So I convert it to a system where I say, okay, well, let me just write down the original again. I have y double prime plus 7y prime plus 10y is 0. If I convert to a system, I'd say, okay, y prime is v, and v prime is, you solve for y double prime. So it would be negative 7y prime minus 10y, but then replace the y prime with a v. So I get negative 7v minus 10y. So I've asked you to do this several times, take a second order equation and convert it to a system, but then we've sort of stopped. We've sort of been done after that. That's the extent of the question. Now, we're going to use the fact that we have lots of tools to analyze a linear system, all the tools from chapter 3, finding eigenvalues and eigenvectors, to actually solve it. So first, I'm going to convert this to matrix form. So this is y prime v prime equals some matrix times yv. So y prime has to equal v. So I need a 0 and a 1 here so that when I dot product, I get v. And v prime is negative 7v minus 10y. So I need negative 10, negative 7, so that the negative 10 goes with the y and the negative 7 goes with the v. So this is the matrix A. And then to find eigenvalues, you find the determinant of A minus lambda I. Solve determinant of A minus lambda I equals 0. Okay, so this is going to be the determinant of negative lambda, 1, negative 10, negative 7 minus lambda. Yeah. And then to find the determinant of a 2 by 2, just AD minus BC. So I have, I'll just write it out, negative lambda times negative 7 minus lambda, AD, minus negative 10. So it's plus 10. Just going to multiply this all out. So I get lambda squared plus 7 lambda plus 10 equals 0. Oh, does that equation look familiar? Yeah, we solved it in method 1, except instead of lambdas, we used s's. It was s squared plus 7s plus 10. So that's not a coincidence, right? In fact, I think in a lot of physics or engineering disciplines, they use the letter s for eigenvalue and eigenvector. For eigenvalue, I mean, instead of lambda, because of the e to the st thing. All right, so we know the solutions to this thing. We get lambda is negative 5 and negative 2. All right, now we got to find eigenvectors. I'm just going to go to a new page, keep it neat. So for lambda equals negative 5, we need to solve AV equals lambda v. Sorry, it's not xy in this case, it's yv. Okay, so this says 1v equals negative 5y. And negative 10y minus 7v equals negative 5v. It's going to be the same, an equivalent equation. So let's come up with a vector that satisfies this. 1, and -5. Yeah, if y is 1, v is -5. All right, and then we'll do the same thing for lambda equals -2. Oops. So this says v equals -2y. And so a vector that goes with that would be 1, -2. I just picked a value for y. Pick 1, then v is -2. Yes, thank you. Okay, so I have eigenvalues and associated eigenvectors. I can now write down my general solution using the e to the lambda t v method. Okay, so my general solution is going to be y of t equals k1 e to the lambda 1 t v1 plus k2 e to the lambda 2 t v2. You have two eigenvalues with associated eigenvectors. So you get two particular solutions, e to the lambda tv, and then take a linear combination. So I'll just put this all in here. And this is a vector. So this is actually yv. All right, is this the same general solution that we got before when we did it the fast way? Lucky guess. It looks different to me. Like, why is it? Yeah, it's vectors. Yeah. So the upper component, the first entry of this vector valued thing is y. The second entry is v. And v is just the derivative of y, right? So let's just parse this out. We'll say pull out the y of t and the v of t. So I just want the first entry. So this is going to be k1 e to the -5t times 1 plus k2 e to the -2t times 1. That is the y that I got before. And then my v is going to be -5 k1 e to the -5t minus 2 k2 e to the -2t. And that v is exactly the derivative of y. I could have, so if I was using my original method, the lucky guess method, as soon as I got y, let's go back here. As soon as I had y, if I happened to also need v, I could just take its derivative because velocity is just the derivative of position. -5 k1 e to the -5t minus 2 k2 e to the -2t. Yeah, yeah. Okay, so now I have the general solution, and I would like to find a particular solution that satisfies this initial condition. All right, so I'm just going to write down the general again. It was yv equals k1 e to the -5t times 1 -5 plus k2 e to the -2t times 1 -2. And I know that y of 0 is 2 and y prime of 0 is -13. This could also say v of 0. Y prime is v, right? So I know that if I put 0 in for my t's here, I should get 2 as the top entry and -13 as the bottom entry in this vector. So I'm going to do y of 0, v of 0, And I'm putting 0 in for my t's. So this just becomes k1 times 1 negative 5 plus k2 times 1 negative 2 equals 2 negative 13. And now I should have two equations with two unknowns here. Take the top entries. I have k1 plus k2 is 2, and negative 5 k1 minus 2 k2 is negative 13. Use your favorite method to solve this. Substitution, elimination, row reducing a matrix, whatever you like. I'm going to do elimination. I'm going to multiply this first equation by 2. So I have 2k1 plus 2k2 equals 4. And then add those together. So I have negative 3k1, the k2's cancel, equals negative 9. Divide by negative 3, so I get k1 is 3. And so k2 has to be negative 1. But then be careful not to just circle your k1 and your k2 and be done, right? They were asking for a particular solution here, so I have to write it out, right? Y of t, b of t equals, and then instead of k1, I put a 3, e to the negative 5t times 1 negative 5. And then instead of k2, I put a negative 1, e to the negative 2t, 1 negative 2.